Alright, so we're going to talk about planes today. We're still in section 11.5. So we're going to talk about planes in space. So let's remember very quickly when we talked last time. We talked about lines, and we defined a line as. So we had a line and we had a point on our line, and we defined our line as a set of all points such that the vector from our point to any other point is parallel to some given vector. And that's how we define the line. So we need a point on the line and a parallel vector to write the equation of our line in space. So we're going to do something similar with planes. We're going to use a point and a normal vector to come up with our equation for a plane in space. So let's draw what we're talking about here. Here's our plane, and here's a normal vector. We'll put our arrow on here. There's a normal vector to our plane, and we have some other vector in the plane. So we're going to call this point here, we'll call this point Q, or sorry, point P. At the end of this vector, we'll call this point Q. We like P's and Q's, and this is our normal vector. So this is a 90-degree angle. So we have our point P, our plane. Plane contains P, and we'll call point P x1, y1, z1. So some specific point. And our normal vector n, we'll say that n is ABC, vector ABC. So we're going to define our plane in space This is going to be our definition. We're going to define the plane as the set of all points Q, and Q is just going to be x, y, z, some arbitrary point in our plane, such that the vector PQ is orthogonal to our normal vector. So if we go anywhere on our plane, if we make this vector PQ, because this is the normal vector of the plane, this is going to be normal, it's going to be orthogonal to any vector in the plane. So we're going to define our plane as the point, as a set of all points Q, such that this vector is orthogonal to n. And this is going to give us the tools that we need to analyze, write the equation and analyze our plane. So if PQ is orthogonal to n, we can say n dot PQ is what? Zero. So our dot product is 0, and this is our vector equation for a plane. N dot PQ equals 0 is our vector equation for a plane. Now we don't normally work with this equation. What we're going to do is just like we did for the lines. We're going to write an expression for n dot PQ and equate components. So I'm just going to expand this out. We're going to say that ABC, the vector ABC, dot PQ, our expression for PQ is going to be x minus x1, y minus y1, z minus z1. I'm just writing an expression for the vector PQ. And that dot product is 0 for all the points x, y, and z, for all points q on the plane. And now I'm just going to expand this dot product, and I get a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. So I just expanded this dot product. This is our standard form for the equation of a plane. And our plane contains points point P, which is x1, y1, z1, like we said before, with our normal vector n. And n is our vector ABC. So, questions on how we came up with our definition and our equations. Now notice our equation for a plane. 1, it's a linear equation. So the equation of a plane in space is a linear equation. The coefficient on x gives us the x component of our normal vector. The coefficient on y gives us the coefficient on, or the y component of our normal vector, and the coefficient on z gives us the z component of our normal vector. And we can regroup terms here. So if I distribute and regroup, I can write this as another way that you'll often see the equation of the plane is ax plus by plus c plus d equals 0. So this constant d, just contains all the terms for our given point a times x1, b times y1, and c times z1. So this term d, it contains all of those combined. But we still have our components of our normal vector. Whoops, I forgot my z here. I still have the components of my normal vector from the coefficients on the x, the y, and the z. So questions? All right. A couple of important things about planes. Distinct planes in space either intersect, they are either parallel or they intersect in a line. So I'm not talking about the degenerate case where two planes are equivalent. So if we have distinct planes, they're parallel or intersect in a line, we can show, I'm not going to go through the process, but we can show that the angle between two planes is the same as the angle between their normal vectors.
That makes sense.
Okay? Right, right. So we're going to say that the angle between planes, the angle between two planes, we'll just use our dot product. Cosine theta is the magnitude of n1 dot n2 over the magnitude of n1 times the magnitude of n2, where n1 and n2 are normal vectors. And just as an extension from this, just because of the properties of the dot product that we've talked about before, if the dot product is 0, then our planes are perpendicular. And if one is a scalar multiple of the other, the planes are parallel. And here C is a scalar. So just because we're from the properties of the dot product, we're using the dot product to define or to come up with the angle between these two planes with these normal vectors. If these conditions hold, this is what it tells us about those planes. Does that make sense? All right. So like we did with lines, one thing that we're interested in with planes is, well, we have our normal vector, we have a vector in the plane. But we want to figure out how to determine the distance between a point that's not in the plane and the plane itself. So let's take a look at how we do that. So let's draw a picture, and our picture will give us some motivation as to how we're going to proceed with this. So here's our plane. Here's our normal vector. And here is, I'm going to draw this point over here, P. Let's make that Q. We like our point P to be on our plane. Here's point P. And this is our normal vector N here. Now, do we remember what we did when we were looking for the distance between a point and a line? How did we go about it? It had to do with the cross product. So
the cross product or the magnitude of the vector.
Right. So let's have to do with the cross product, the magnitude of the cross product. So let's draw a vector here. Since we're using vectors, we're in space. We're using vectors. So I'm going to draw a vector to point Q. And now I'm going to project this down. So let me do this. I'm going to project this down onto the plane, like so. And I'm going to draw this little right triangle, like so. and this is a 90-degree angle. And this is the distance that we're looking for. The distance between Q and our plane. And I'm going to draw one other little projection over here, like so. Like this. All right, now that I've drawn this diagram, does anybody have an idea of how we might go about this? How do we find this distance d? Perfect. The distance d is the magnitude of the projection of PQ onto our normal vector. This distance is d here, this distance is d here. So this little piece here is the projection. If I make a vector here, that vector from P to where my projection hits our normal vector is a projection onto N of PQ. And our distance is the magnitude of that projection. So D is the magnitude of the projection onto N of our vector PQ. And how do we find the magnitude of this projection? Remember how what we did to find the magnitude of that projection? So I'm going to write this out. D is the magnitude of projection onto N of PQ. It's a dot product. That's PQ dot N. And we have to do one other thing. Divided by the magnitude of the normal vector. So this is how we find our distance between a point and a plane. P is a point in the plane. Q is the point that we're interested in. Q is not in the plane. And N is the normal vector. So for a line, to find our distance, we use the cross product. For a plane, to find the distance, we use the dot product. We can choose any point in the plane to form our vector PQ, and we end up with the same result. We might get a slightly different expression for our distance, but when we solve it all out, we should come up with the same answer. All right, so let's look at some examples. Any questions before we go on? All right. So we want to let me pick a couple here. What do we want to do? Let's do a very easy one first. We want an equation for the plane through our point P is negative 307. And with a normal vector, is 5i plus 2j minus k. So if we have our points and we have our normal vector, most of our work is already done to find our equation for a plane. So our coefficient on the x's is 5. So we just pick out our coefficient from the normal vector, and 5 times x plus 3, x minus whatever point we're given. Our coefficient on the y's comes from the y component of the normal vector, y minus our given point, 0, and minus 1 coefficient. Our z component gives us our coefficient on the z's, minus 1 times z minus 7, and this equals 0. And I can expand, I can distribute and rearrange, and I could write, if I rearrange this, I get 5x plus 2y minus z equals minus 21. So this would be our equation for this plane through point -307 with this normal vector. So once you have your points in your normal vector, your work is almost done if you're just looking for... What's that? 15 plus 7, yes. Should be 22. Thank you. Questions? All right, another example. A little trickier. We want the equation for the plane. Our plane contains the point A0, 0, 1. The point B is 2, 0, 0. And the point C, which is 0, 3, 0. So we need a couple of things for our equation. We need a point on the plane. Well, we have 3 points here, and we need our normal vector. How are we going to find a normal vector? Cross product. We can make a vector from A to B and a vector from A to C, form their cross product, and that's going to be perpendicular to the plane. It's going to be orthogonal to each of those vectors. So we can find the cross product. And we can do any combo of vectors from one point to another point. So I'm just going to say that our normal vector is going to be the cross product. I just chose AB cross AC. And that's going to be my normal vector. And then I can use any of these 3 points once I find my normal vector. I'm not going to go through all the calculations. We just have to form our vector, form the cross product to get our normal vector, and then do the same procedure we did here. Our coefficients come from the components of our normal vector, and we can pick any of those 3 points to be our point in our plane to write our equation. Does that make sense? Okay. Let's do a distance problem, and then I just have a couple of things things to expand on, and then we're done. So we'll do a distance problem next. We want the distance from Q is 1, 1, 3 to the plane 3x plus 2y plus 6z equals 6. So here's our point that we're interested in, our point that's not on the plane. Here is our plane. So what things do we need to proceed with our problem? We need our normal vector,
Point on the plane.
and we need a point on the plane. So our normal vector, so we need those two things. We need our point on the plane. For our distance, we need a point on the plane, point not on the plane, and our normal vector. So our normal vector n in this case is what? The vector 3, 2, 6. We just pick out the coefficients on x, y, and z. So there's our normal vector. How are we going to get a point on the plane? Anybody have an idea? You could plug in some values. So what would be easy values to plug in? 0, 0. So if we pick x, we pick x as 0. If y equals 0, then z has to be 1 to satisfy this equation. So our point on our plane is the point 0, 0, 1. And that's a nice easy one to work with. So now we can find our vector PQ. So PQ is going to be what? 1, 1, 2. So we're just forming the vector between P and Q. And now we can find our distance. We're going to do PQ dot n. PQ dot n is going to be the vector 1, 1, 2. And we take the dot product with 3, 2, 6, and our dot product comes out to be, what do we get? 3 plus 2 plus 12, so we get 17. And the length of n, or the magnitude of our normal vector, is going to be the square root of 9 plus 4 plus 36. Which equals 7. So our distance B is 17 over 7.
I know from before that the distance equals dot product. I have magnitude. Magnitude of dot product?
Right. So if your dot product can come out to be negative.
Oh, okay.
So we take the absolute value.
Okay, so absolute value.
Right.
Yes. Not magnitude.
Right, because the dot product is a scalar. I said magnitude, but the magnitude of a scalar is just its absolute value. So the dot product's a scalar, so we want our distance to be positive, so we take the absolute value of it. So our distance is going to be 17/7 units. Now I'm not going to go through this whole thing. But I want you to think about this problem and how we would go about it, because this is one that people often make mistakes on. So I just want to think about how we're going to set this one up. We want to find the distance between parallel planes, x plus 2y plus 6z equals 1, and x plus 2y plus 6z equals 10. And I'm going to say that it is, B does not equal 9. So these planes are parallel. So the reason their distance doesn't equal 9 is if I make a quick sketch here. Here are my two parallel planes. This shifts our planes this way. So this would be 9. And we're looking for this distance. So how would we go about solving this problem? Find a point on one of the planes, and then, perfect. So what we're going to do if we're looking for parallel planes, what Med said is we're going to find a point on one plane and just treat that as the point that we're interested in. And then we'll find the distance from the other plane to that point. So we're going to find a point Q on one plane, and then we're going to find the distance between the other plane and the point Q. So for the other, we can use the normal vector for the other plane. We can form our vector from a point on the other plane to Q, just like we did in our previous problem. We can find some point on the other plane, form our vector PQ, use the dot product, magnitude of the dot product over the length of our normal vector. Does that make sense? All right. This one. Every year when students see this one, they're going to say, there are students that will say, "Oh, that distance is 9." But we're looking for this perpendicular distance. All right. The last thing I want to mention is there is a formula. If you like formulas, I don't like to memorize formulas, but there is a formula that we can use for the distance between a point and a plane. So what we're going to do is I'm going to take the expression that we came up with before, D equals the absolute value of PQ dot n over the length of n. And I'm going to apply this to a point some arbitrary point Q, which we'll say is x0, y0, z0. So this point Q is the one that we're interested in, the one that we want to find the distance from the plane to this point. So we're going to apply this to this vector equation to this point Q. And point P is in the plane. P is x, y, z. Why don't I do x1, y1, z1 since we have the subscripts here. So I'm going to write and plug these values or these variables in and use them in our expression for PQ and rearrange this to get that our distance, if I have a point Q not on the plane, a point P in the plane, our distance is the absolute value of AX0 plus BY0 plus CZ0 plus D over, and we'll write what D is in just a second, over the square root of A squared plus B squared plus C squared, and I should write N. Our normal vector is the vector ABC. And D is negative AX1 plus BY1 plus CZ1. So if you want a formula that you can just plug and chug into, this would be your formula. I prefer to work with this. It makes sense to me just in terms of how we're coming up with our distance. And this helps me visualize what I'm doing. But if you want a formula that you can just plug numbers into, this would be your formula for your distance. And all we've done to get this is just plug these points into this expression and write everything out explicitly. Any questions? Okay. Your homework. Page, we're on 805. And I want you to, on page, read, on page 802, sketching planes in space.
Is the view that just like you have one chunk of the plane and you assume that expands out infinitely with sketching planes?
Sketching planes, right. The gist of it is if you let x and y equal 0, you can get a point on the z-axis. If you let y and z equal 0, you get a point on the y-axis, etc. So you can make a little kind of a little triangle shape on the first quadrant, right in the first quadrant, and then you're assuming that it extends out infinitely. Is the gist of it. But rather than me going over it, if you read it, the book does a really good job of explaining the process. All right.